Hi, I'm Akhil Puri and I will be presenting the findings of our research course project for time series modeling using tools and methods delineated in our time series coursework. The research question at hand deals with fitting a suitable time series model to a public dataset, which in our case is the daily PM2.5 particulate matter observed in Beijing, China. PM2.5 are fine particles which have a diameter measuring 2.5 micrometers or less. Particles of this size are typically chosen as indicators of air quality due to particle size and respiratory risk being inversely correlated. That is, smaller the size of the particle, the higher the respiratory risk. Beijing has long been considered as one of the most polluted cities in the world with the most toxic air quality index. That has changed over time due to certain policy changes brought in by the government to rectify this long enduring reputation of being one of the most polluted cities, but still hasn't been enough as the lowered index still averages 4 times the desired level of 10 micrograms per meter cube as set out by the World Health Organization. Now, without wasting any more time, let's get into the description of the data and our findings. The data has been sourced from iqair.com and is from the 1st of January 2014 to the 21st of May 2020. The plots shown here are daily time series of PM2.5 and the corresponding QQ plot to test whether the data is normally distributed or not. What we can see is that the daily data is not normal with massive deviation of the tails. The time series is heavily clustered and bunched, which will not help us uncover suitable insights in terms of model fitting and eventual forecasting because of the problem of overfitting. We do not want too many terms for the number of observations because when this occurs, the regression coefficients will represent the noise rather than the genuine relationships between the variables. Another issue with complex overfitted models is that a model tailor-made to fit the random quirks of one sample is unlikely to fit the random quirks of another sample. Thus, overfitting a regression model reduces its overall generalizability outside the original dataset. Hence, what we propose is aggregating the data month-wise to glean clearer insights, which brings us to the visual analysis of the data. What we now present is the visual analysis of the data, that is the time series plot for aggregated monthly values, the lag plot which shows weak correlation between the series and a lagged version of itself, and the ACF and PSEF plots which show significant correlations at lags 5 and 6, suggesting an autoregressive and moving average component in the series. Further lack of a decaying pattern in the ACF does not provide enough information about the stationarity of the series. But what the ACF does suggest is a stochastic trend, as the spikes do not occur at set intervals, suggesting that there is no seasonality in the data, which is further corroborated by the labeled time series plot. If we focus on the time series, what we can see is changing variance, suggesting non-stationarity, which will require transformation to stabilize the fluctuations around the mean level. There appears to be a downward drift in the mean trend, but what is clear from the series is the presence of both succeeding points as well as fluctuations, suggesting both AR and MA components. P-value of 0.5906 from the ADF test confirms the non-stationarity that we were suspecting earlier. Moving on to the model specification part, we can see that the transformation and first order differencing has resulted in a more stable series upon visual inspection. The ADF test of the difference series gives us a p-value of 0.01, which is more than significant to reject the null hypothesis that the series is non-stationary, or accept the alternate, which is that the time series is stationary or trend stationary. What is worthy of attention here is the spike at lag 1 in the ACF. Significant correlations at the first or second lag, followed by correlations that are not so significant, suggest a strong MA component, and the number of significant correlations in the ACF indicates the order of the moving average term, which appears to be 1, though this is just a general guideline with the actual order to be ascertained through parameter estimation in the way of significant coefficients, AIC and BIC values, and the check for overfitting. Coming to the PSCF, what we can see are significant correlations till the fifth lag, followed by correlations that are not significant, suggesting an autoregressive term as well in the series. This number of significant correlations indicate the order of the autoregressive term, which through visual inspection is 5, but like I said earlier, we need to conduct further analysis to determine the most suitable order. Broadly, through visual inspection, we narrow down to ARIMA 011 313, 413, 513, 514 after analyzing both the EACF chart and the BIC table for model selection. We keep the lower order model 011, keeping in mind the principle of parsimony. Coming to parameter estimation, we use two methods, the maximum likelihood and conditional sum of squares. Though maximum likelihood is the preferred method, we will be using both to determine which model is returning significant coefficients for the order of AR and MA components. Maximum likelihood maximizes the log likelihood function of the ARIMA model, whereas CSS minimizes the sum of squared residuals. From the table, we can see that ARIMA 011, 313, 413, 513, and 514 have significant coefficients for the highest orders of AR and MA components. The positive sign is for the significant coefficients. The negative sign is for the insignificant ones. The lowest BIC score is returned by model ARIMA 514, followed very closely by 513. So we will be considering both for residual analysis diagnostic checking. Coming to the overfitting check, to ensure that ARIMA 514 and 513 are adequately complex and is not underfitting the time series, ARIMA 614 and 515's performance will be modeled. Upon further investigation, it was found that model ARIMA 614 has an insignificant MA4 coefficient and ARIMA 515 has an insignificant MA5 coefficient. Since overfitting ARIMA 514 and 513 returns insignificant coefficients, we stick to these two for residual analysis. Residual analysis is a series of tests to ensure that the residuals of our selected models behave like white noise, with no autocorrelation between them, implying that our models have fitted the data well. To verify these models, three properties of white noise need to be examined. Firstly, the tests include a time series plot of the residuals to ensure that the residuals display stationarity with zero mean, constant variance, and a random overall pattern. Secondly, QQ plot histogram and the Shapiro-Wilk test to ensure normality of residuals. Lastly, the inspection of ACF and PACF to determine whether residuals are autocorrelated or not. When all three properties are satisfied, the model is then considered appropriate to forecast. Both our models, ARIMA 514 and 513, passed the residual analysis check for normality using QQ plot and histogram and showed no significant autocorrelation for any of the lags in the ACF or PACF. We finally choose ARIMA 514 as a good fit because of lower BIC score and the fact that ARIMA 513 was underfitting. Our final goal is for the residuals to pass the Leung box test. In failing to reject the null hypothesis with a p-value greater than 0.05 for all the lags, which helps us select ARIMA 514 for forecasting purposes. The forecast over the next 10 months appears to suggest that there won't be a significant change in the PM 2.5 levels when compared to that of 2019, with it remaining relatively steady at around 150 micrograms per cubic meter. The level of variance also appears relatively equivalent to that of 2019. Although efforts by the Beijing authorities have seen the PM 2.5 levels almost halved since 2009, the forecast would suggest, however, that to continue this improvement in air quality, further measures shall be required. With the current measures in place, it would appear that the air quality will only be maintained rather than improved. This concludes our presentation, and thank you for listening.